that light source direction, right? So for some constant cosine of I or some constant theta of I, that's a cone around the illumination direction, all right? Well, I can project, remember, PQ space allows me to map any direction, any surface orientation, to a PQ location, right? So I'm going to project that constant cone up into PQ space, and I'm going to get this elliptical, it's not really an ellipse, I'm just going to get this cone sliced by a plane. And the idea is that everywhere along that curve is the same cosine angle between the surface normal and the source direction. So that means that it's equally bright. Those are referred to as isobrightness contours in PQ space. That's a lot to say. But basically, along that curve in PQ space, I get the same intensity because that curve represents the set of possible angles that are the same cosine theta away from the source direction. Look at that a little more carefully in PQ space. Let's assume that we've got some source PQ that's right here. All right? So if my surface normal were pointing right at that direction, so the theta I is 0, cosine I is 1, then my value would be 1. All right? But suppose cosine is 0.9. All right? Well, that would be some curve, draw it around here, right? This is some isobrightness contour, so every one of those PQs would give a intensity of 0.9. Going out a little further, 0.8, 0.7, gets even further out, 0.6, 0.5, right? Here's all the way down to 0.3. And then finally, what happens when we get to a point where the surface normal is perpendicular to the light source? Well, if the surface normal is perpendicular to the light source, the cosine of theta I is 0, so no light is hitting that surface, okay? And so that would be this line here, right there, where it's a 0 value, because that's the equation of a line in PQ space, right? P times PS plus Q times QS plus 1 equals 0. That's like AX plus BY plus C equals 0 in the P, but it's in PQ space, so it's AP plus BQ plus C equals 0, so it's a line. So the perpendicular situation is a line in PQ space. So, and notice, by the way, that the R of PQ is a maximum right when the surface normal lines up with the light source, as you might expect. So that's our reflectance map in the Lambertian situation. How about shape from a single image? So given R of PQ, so that means that we know where the light source direction is and we know the surface reflectance, so we can eliminate that or assume it equals to 1. Can we determine PQ everywhere, the surface orientation, uniquely for every image point? So here we have, some random point, and maybe its intensity compared to the brightest point is 0.7, so it's somewhere on that curve. But it's somewhere on that curve. I don't know exactly where it is in that PQ space. So no, I can't sort of just simply from this analysis be able to determine the total shape or the orientation at every location. So if I want to do this, if I want to compute shape from a single image, how might we do that? Well, basically this is an example of an ill-posed problem, and we need some additional constraints. We need some additional information, like the lighting is known, or boundary condition, or maybe even other information. And in fact, there are sort of two standard moves to make. Basically, one that doesn't really work and one that does. The one that doesn't really work, which we'll talk about in just a minute, was the traditional shape from shading, and that is we're going to add some additional constraints. And the one that does work is you actually take more images with different light sources illuminated, and that's called photometric stereo. That has some real applicability. So let's first talk about traditional shape from shading, where you add more constraints. Remember, here is our question. Given a single image of a known surface reflectance, so we know the albedo, with a known light source, can we recover its shape? As we said, that means given that RPQ, can we determine PQ everywhere? And the answer is, well, I have to cheat a little. No, not cheat. I have to make some assumptions. Assumption number one is that, for example, at this boundary, which is already drawn in red, I'll do it again, we're going to assume the shape is known. And in fact, what you can imagine is that everywhere at this boundary, because it's falling off, I know that the surface normal is 90 degrees from the camera. So I know something about the surface orientation. Then the other thing that I'm going to assume is that the surface is integrable. What that means is, remember, I'm recovering orientation. Well, orientation you can think of as the surface derivative. Well, the whole thing has to integrate to a depth value. Okay? And then finally, I'm going to assume some sort of smoothness, and I'm going to put this whole thing in some form of an optimization method. Back 100 years ago, I did a paper with Yvonne Leclerc called Direct Height from Shading, I think it was called, which attempted to not do it quite so much in a orientation-based way, but directly in a height way and take the derivatives. It was, we were running on a connection machine. But basically, the idea was to recover the full height from this image under these relatively restrictive assumptions that you know the albedo everywhere, that you know either the depth or the orientation at some particular contour. We actually used stereo at the contour to get that initialization, then we did shape from shading in between. If you look up shape from shading, you'll see a lot of pictures that look like this, and these are typically synthetic results. So given some depth map, you can make some sort of a shaded image, and then you can show that you can recover the shape that's really there. Unfortunately, one of the reasons they show synthetic results so much is that the results on real images are somewhat, shall we say, less than wonderful. In fact, there was a paper by Mubarak Shah and some students, I think in the late 90s, early 2000s, where I think the phrase was something like, well, it works poorly in the lab and not quite as well as that in real life. You know, basically, and why is that? Well, the problem is these assumptions are overly restrictive. I mean, a constant albedo everywhere, that means you get no variation in the color or the underlying texture of what's there. You know, knowing about the light source, the orientation directions, it's a very brittle type of computation. So what can we do instead? Well, what we can do instead is we can take more images. All right. And this is what's referred to as photometric stereo. So the idea is that we take picture from the same camera location. So we can still have Z as a function of X, Y, same object, but with different lighting. So here we have the picture taken from the same location with different lighting directions. And what we want to get out is this, right? The Z is a function of X, Y. And unlike traditional shape from shading, with enough lights and sort of careful calibration, etc., we can also recover the albedo, the reflectance function at every point. So now we don't have to make this overly restrictive assumption that the color or the reflectance of the object is the same everywhere. We're allowed to let it vary. Let's go through this algebraically. So here we have our camera, which has some viewing direction, all right? And the viewing direction is not going to matter because we're going to assume a Lambertian system, which is what we have here. We assume that it's just proportional to the cosine of the incident angle between the light source and the normal. But the idea is that the camera is fixed. And for each one of our sources, source 1, we take our first image. Source 2, we take our second image. Source 3, we take our third image. Now notice, by the way, that rho is in these equations, right? Rho is the albedo. So I'm not assuming I know the albedo. So now I have 3 images. Right? And I can write these as a matrix equation for, this is for a single pixel, right? So at a single pixel, I would have 3 different values, and I could just write this equation as rho, and these are the 3 vectors that are the source directions. And by the way, I assume I know the source directions, times the unit normal, and the unit normal is the thing that I don't know. So I need to solve for that, all right? So remember, we're making this Lambertian assumption. So solving those equations is straightforward. It's linear. It's a simple linear system if we have 3 lights. I is our 3 measurements, 3 intensities. S are the 3 directions to the light source, and we know those, so I and S are known. And then, as we said before, N is supposed to be unit normal, rho is the albedo. So together I call them N tilde. So to solve for N tilde is trivial. N tilde is just S inverse I. But of course, N tilde is not a unit normal. In fact, its magnitude is what? Its magnitude is the albedo, so I can solve for rho, the albedo, and I can solve for the unit normal as well by just taking the magnitude of that. Now, of course, that's with 3 lights, and anything that works well with 3 lights is going to work better with more lights. So let's suppose we have more lights, like m of them. Well, we get the same set of equations, but now we need a least squares solution because the system is over-constrained, and basically solve it here. So m by 1 is the number of measurements we have, and so we have to take the pseudo-inverse. And the pseudo-inverse will give us the least squares solution for n tilde, and then again you can find the albedo. That was the algebraic approach to the solution, and it works nicely. In fact, that's the math that you would actually encode if you were writing a computer program to do this. But what it doesn't do is give you exactly the intuition of what's going on in photometric stereo. So to do that, let's take a look at this in PQ space. So let's suppose we have some light source, the first light source PS1, QS1. And so we'll say that, remember, we know where it's located. And then if we measure its intensity, let's say it's 0.7, that's some particular curve here. So the other ones are dotted to remind you of them. But the idea is that the solution for P and Q must lie somewhere on that curve, right? We don't know where yet. So what do? Well, in the old shape-from shading, we did some funny sort of assumptions and integration and stuff that just doesn't work. Well, here all we do is we say, let me put up another light source. Here is the second light source, PQ of 2 of S, and now it has to lie somewhere on this curve. Okay, you'll notice those curves intersect in more than one place. Well, that's troubling. It intersects more than one place. What do we do to make it come to one place? Well, we just put down a third light source. All right, and if everything is calibrated and working correctly, then the orientation of that point and the albedo are recovered at being exactly that location. So that's the geometric sort of description of photometric stereo. A simple example is shown here. Here is a sphere. You can sort of tell that it's a sphere, right? It falls off down here, so we're looking straight down, with 5 different illuminations. When we do photometric stereo on that, remember, we can recover both surface normal and the albedo. And that's what this looks like here, right? So the albedo, you can see that it recovered the fact that it's got these 4 quadrants. So even though this thing falls off slowly, it knows that it's all the same albedo. And then this is the estimate of the surface normals. And so this is what's sometimes called a needle diagram, where you're looking at where the needles are pointing. That's the surface normal. Now you can actually do this somewhat for real. So here's an example where there are 4 input images. So the lighting is coming from different directions. Right? You can see here you get different kind of shading, right? And it recovers both the albedo, which is sort of the paint, the color, and you can see that it actually knows that there are these stripes on there along with the surface normals. So it recovered the shape. In fact, there's a really cool app you can download from this company called trimensional.com, and this is not a commercial endorsement. It's just a Georgia Tech endorsement. This was an app put together by Grant Schindler, where you basically take your, I don't know if he's got it on Androids now as well, but certainly at the time it was on iPhones, and you take pictures from different locations, and it uses the light to illuminate it, and it does a surface reconstruction. All right? And it works pretty cool, and download it, and I think it's it might be free. I know it might be $1. Maybe it's $4. Whatever it is, if you buy it, Grant, send me money. Okay, so photometric stereo is used in a couple of interesting applications. It does have some challenges, like you have to know the reflectance function. You have to know that reflectance map. So typically it's assumed for Lambertian types of stuff, maybe a little bit of specularity, but basically you have to understand the reflectance function. It also has a problem with shadows or inner reflections because it's assuming that the only thing that matters was the orientation of the surface with respect to the light. There are some smaller problems, like the cameras and light sources have to be far enough away that it's a constant angle. That's not so bad. Calibration is important, right? Remember, we're assuming that everything is linear in terms of the intensity with respect to the light that's hitting the camera. So you need a lot of photometric calibration. Before I conclude, a couple things about some shape from shading. One is there was a really cool use of it. There was a paper, actually won one of the Marr Prizes in 1995 in ICCV, and it was this idea. The name of it is shape from shading with inner reflections under a proximal light source distortion-free copying of an unfolded book. And it appeared later in IJCV, International Journal of Computer